Roll time backward until numbers lose meaning, temperatures trillions of degrees, densities that fold light itself. In that embryonic flicker, the universe knew no distinctions. Forces we separate into gravity, electromagnetism, and the nuclear siblings merged into one super interaction. Quarks, leptons, gauge bosons, every particle was a massless note in the same blinding chord. Identities erased by heat. Physicists call this epoch grand unification. In particle accelerators, we see hints. The running strengths of the strong, weak, and electromagnetic forces nearly converge if we extrapolate to energies around 10 to the power 25 electron volts. Beyond that summit, their mathematics may fuse. Described by elegant groups like SU5 or SO10, glimpses remain speculative. But cosmology agrees on the texture. A perfectly symmetric field filling space, smooth as still water, yet storing stupendous potential. The symmetry that complete is fragile, supercooled metal ready to crystallize. The early cosmos awaited the slightest imperfection to shatter its uniformity. Quantum fluctuations, tiny foam-like wiggles, were already whispering beneath the glare, preparing cracks that would let structure bloom. The stage was set. One decisive drop in temperature, and the universe would never be the same again. At 10 trillionths of a second, cosmic temperature dipped below a critical 10 to power 15 Kelvin. And the smooth field that once unified electromagnetism and the weak force wavered. Picture a perfectly round tabletop with a shallow ridge encircling its edge, the Higgs potential. While the universe blazed above the ridge, everything remained centered. Cooling nudged the field. Like a marble on that table, it rolled off the peak and settled into the circular valley. One moment of off-balance and symmetry snapped. This simple displacement rewrote reality. The photon stayed massless, free to roam as light. Its cousins, the W positive, W negative, and Z bosons, suddenly shouldered nearly 100 proton masses. Their range compressed to the heart of the atom, defining the weak force's feebleness. Quarks, previously weightless, gained heft proportional to how tightly they coupled to the Higgs field. Electrons followed suit. Mass, once an abstract potential, crystallized into measurable inertia. Laboratory echoes of that snap appear whenever a Higgs boson materializes at CERN, living for a tiny fraction of a second before decaying in sprays of bottom quarks or photons. Brief reminders of the moment the universe chose a direction in an otherwise featureless field space. Without that tilt, atoms would never bind, stars would never fuse. And Symmetry's perfect hymn would have remained beautiful, yet mute. It's offering no stage for chemistry, planets, or wondering minds. Microseconds ticked. The universe cooled to 2 trillion Kelvin, and a second symmetry yielded. The strong force, quantum chromodynamics, once let quarks flit freely in a glowing quark-gluon plasma. But as temperature dropped, chirosymmetry fractured, and the color field tightened like an elastic net. The high-energy freedom of quarks gave way to confinement. Flux tubes of color snapped them into permanent triplets and pairs. Out of that lockdown emerged the first permanent matter, protons and neutrons. Burdened now with most of their mass not from quark heft, but from the kinetic frenzy caged within. A sea of lightweight pions, born as the Symmetry's Nambogold stone messengers, who flooded space and quickly decayed, leaving behind an inventory of hadrons that would later assemble into nuclei, stars, and storytelling brains. Today, heavy-ion colliders, like RHIC and the LHC's ALICE detector, recreate droplets of that newborn plasma. Sensors record jets of hadrons spraying from collisions. Each jet evidenced the confinement reasserted itself less than a yoctosecond after liberation. In those collisions, we read a fossil memory of the cosmic kill confirming that mass, and ultimately the solidity of mountains, rose not from quarks themselves, but from the broken symmetry of gluon fields freezing into color-neutral knots. Even earlier another field, the inflaton, hovered at the crest of a nearly symmetrical plateau. For reasons we still puzzle over, that plateau was almost, but not perfectly, flat. The slight downward tilt set off inflation. Space-time, spanned by a factor greater than the atomic radius ballooning to the size of the Milky Way, all in a breath of cosmic time. Like a flawlessly still lake suddenly whipped by wind, Quantum fluctuations on microscopic scales stretched into macroscopic ripples. Inflation solved riddles that once taunted cosmology. Why is the universe so smooth across regions that never shared light? Because those regions were once neighbors before inflation yanked them apart. Why is space so flat, sitting at critical density? Because any curvature was ironed out the way a balloon's surface flattens as it inflates. Eventually the field rolled off its plateau, symmetry breaking again as inflation halted. The inflattened's potential energy transmuted into a hot bath of particles, heating the universe and setting the stage for Electroweak symmetry breaking, and later the QCD freeze. The density ripples, frozen quantum whispers, became the seeds of galaxies etched as temperature freckles in the cosmic microwave background. Modern telescopes, like the South Pole's Bicep Array, sift that microwave light for the faint curl of primordial gravitational waves, a signature of symmetry almost kept, then spectacularly broken to forge the large-scale architecture of everything we see tonight. When the cooling cosmos reached 1 trillion degrees, matter and antimatter should have annihilated in a final, perfect flash, leaving nothing but stray photons. Instead, for every billion pairs that mutually erased, one lonely proton survived, and every atom in your body descends from that minuscule surplus. What tilted the scales? A conspiracy of broken symmetries known as baryogenesis. Physicist Andrei Sakharov laid the conditions. You must violate baryon number, disturb thermal equilibrium, and most crucial break CP symmetry so that reactions favor matter over antimatter. In everyday physics, CP holds with iron grip, but in the weak interaction, it slips. Neutral kaons observed at Brookhaven in 1964 decay into pions, slightly more often in one mirror twin configuration than the other. Later, beam assaults at SLAC and Keck repeated the asymmetry. Tiny, yes, but in the cauldron of the early universe, even a 1 part in a billion bias was enough. One candidate mechanism is leptogenesis. Heavy right-handed neutrinos decay out of equilibrium. Breaking CP and Sphaleron processes trade lepton excess for baryon excess before Electroweak symmetry fully freezes. Another possibility lurks in undiscovered particles that skew decay channels just so. Experiments at LHCb and Bell 2 now sift trillions of beam-son decays for anomalies. While neutrino-less double beta studies hunt lepton number violation that could confirm the leptogenesis script. Whatever the agent, the lesson endures. An almost imperceptible fracture in symmetry is stamped on every star, planet, and strand of DNA. A cosmic preference that made something instead of nothing. Symmetry seldom breaks without leaving fingerprints. As the universe cooled through successive phase changes, it risked knitting geological scars into space-time itself. Topological defects. Imagine cooling water into ice. Crystals form with misaligned facets, creating grain boundaries. In the grander cosmic crystal, analogous flaws emerge. A misorientation in a unified field could freeze into a magnetic monopole, a north pole without a south. A scalar field choosing left while its neighbor chooses right traps a domain wall, a vast membrane of trapped energy. Lines where field phases misaligned can freeze into cosmic strings. Ultra-thin filaments denser than neutron stars and stretching across galaxies. Inflation likely diluted most defects, but not necessarily all. Modern radio surveys and pulsar timing, arrays scan for the rhythmic shiver of gravitational waves that vibrating cosmic strings would emit. The recent nanograv signal a low-frequency hum teases at such relics. Though astrophysical explanations vie for the podium, future detectors, LIGO Voyager, and the spaceborne LISA antenna may resolve the spectrum and decide. Even if strings hide, their mathematics guides condensed matter labs, vortices in superfluid helium, flux tubes in Type II superconductors, and skymions in magnetic lattice all map onto cosmic string equations. The universe, it seems, practices its grand designs on every scale from tabletop cryostats to intergalactic webbing. Each scar a reminder that perfect symmetry, once broken, never quite heals without a trace. Today's physicists comb the cosmic attic for leftover clues of those symmetry-shattering moments. Down a 700-meter shaft in South Dakota, the Lux Zeppelin detector waits for a dark matter particle to nudge its vat of liquid xenon. Testing theories that add hidden dark symmetries to the standard model. Under the French-Swiss border, CERN's LHCb counts the decays of beauty mesons, checking whether matter still favors itself over antimatter by a hair more than the textbooks allow. Elsewhere, ultra-cold neutrons linger in magnetic bottles, while researchers measure their electric dipole moment. Even a shift smaller than 10⁻⁻28 would expose a fresh violation of CP symmetry, and perhaps the mechanism that set the primordial matter surplus. Radio telescopes join the chase. The CHIME and Hyrax arrays monitor fast radio bursts, whose dispersion patterns could imprint interactions with axion-like particles. Hypothetical remnants of a symmetry broken so softly we have never heard its whisper. Gravitational wave observatories, too, now double as symmetry sleuths. A network of Earth-sized pulsar timing baselines listens for nanohertz ripples that tangled cosmic strings would release, while LIGO Voyager's cryogenic mirrors will probe the kilohertz band for echoes of hidden sector phase transitions. Each non-detection sharpens theory's focus. Each anomaly hints the universe still keeps secrets stitched in broken patterns waiting to be read. Imagine if symmetry had remained flawless. Photons would sail unimpeded through a sea of massless quarks and leptons. No atoms, no chemistry, no color. It is the missteps that give the universe texture. The Higgs fields tilt grants particles inertia, allowing electrons to orbit nuclei instead of racing off at light speed. The QCD freeze locks quarks into protons and neutrons, whose slight mass difference lets the neutron decay. Freeing energy that powers stellar alchemy, further asymmetry arranges electrons into shells, carving the periodic table staircase. Sodium flares in street lamps. Copper conducts music to headphones. Iodine guides hormones. All because a symmetric quantum equation bent just enough to let orbitals vary. On grander scales, inflation's stretched fluctuations gather baryonic matter into filaments, birthing galaxies that churn heavier elements in their cores. Those metals seed rocky planets where broken molecular parity chooses left-handed amino acids and right-handed sugars. Tiny prejudices that let enzymes snap together with exquisite specificity. Thus, the cosmos is not merely tolerant of imperfection. It is dependent on it. Symmetry lays the framework. Symmetry colors the canvas, ensuring a sky peppered with galaxies. A table of elements rich with possibility, and a biosphere capable of asking why the balance is so artfully off-center. The universe's deepest dramas played out in fractions of a second, but their signatures echo into every snowflake and sunlit crystal today. The same mathematics that governed the Higgs field shapes water molecules into six-fold stars and arranges carbon into hexagonal graphene sheets strong enough to suspend a cat on the width of a human hair. In Part 4, Beauty, Patterns, and Snowflakes, we will descend from cosmic furnaces to the everyday artistry of symmetry. How translational order in salt yields transparency in halite. A band structure symmetries let silicon switch your phone's logic. And how life itself exploits chiral preference to build spirals of DNA that archive memory across generations. We leave the roaring early universe and step into a quieter, colder realm where symmetry is no longer shattering but tessellating, assembling snowfields, cathedral arches, and the whorls of a sunflower. The grand laws remain, but now they whisper in ice and petals, reminding us that every breath we take owes gratitude to a cosmos that found its beauty not in perfect mirrors, but in mirrors artfully cracked.